Hello students, let us start our new session of chapter 10, Mechanical Properties of Fluids. Now let us understand how hydraulic machines work. Hydraulic machines are working based on the principle of change in pressure on a fluid. For that, let us consider one horizontal cylinder with a piston and 3 vertical tubes at different points. The pressure in the horizontal cylinder is indicated by the height of liquid column. It is necessary the same in all. If we push the piston, the fluid level rises in all the tubes. Again, in all the tubes, fluid level reaching at the same level. When the pressure on the cylinder was increased, it was distributed uniformly throughout the tube. So, whenever the external pressure is applied on any part of the fluid contained in a vessel, it is transmitted undiminished and equally in all the directions. So, this is based on the Pascal's law of transmission of fluid pressure. It can be utilized in many applications. Here, in this diagram, as you can see, the hydraulic lift, where 2 pistons are separated by the space which is filled with the liquid. Here, this is working on the principle of transmitting pressure. A piston of small cross-section area A1, it is used to exert a force F1 onto the liquid. So the generated pressure P equal to F1 by A1, that is transmitted throughout the liquid towards the cylinder attached with the larger piston A2. So at that area A2, the upward force will be generated. That force will be P into A2. So the piston now is capable for supporting a large force F2 that would be equal to P into A2. And the pressure is generated by the first end of piston at area A1, that is F1 by A1. So here substitute the value of pressure. So here we are able to get F2 equal to P into A2 equal to F1 into A2 by A1. So if we are changing the force at A1, then platform will be moved upward or downward side, which generates the force increased by the ratio of A2 by A1. Now, let us understand another application, hydraulic brake, as you can see over here in the diagram. Hydraulic brake is also working on the same principle of transmission of pressure. When we apply a little force on the pedal with our foot, the master piston moves inside the master cylinder and pressure caused in transmitted through the brake oil, which act on a piston of larger area. So larger force acts on a piston and it pushes down, expanding the brake shoes against the brake lining. So here a small force on the pedal produces a larger force onto the wheel. So the pressure set up by the pedal is transmitted to the cylinder attached to the wheels, so that braking effort is equal on all the wheels. So this is how, just by applying a pedal the transmission of pressure will be exerted onto the wheel and brakes can be affected. Let us go through the example regarding the same. Two syringes of different cross sections without needle filled with water are connected with a tightly fitted rubber tube filled with water. The diameters of the smaller piston and larger piston are 1 cm and 3 cm. First, find the force exerted on the larger piston when a force of 10 Newton is applied to the smaller piston. And second, if the smaller piston is pushed in through 6 cm, how much does the larger piston move out? So here, based on the fundamental of transmission of pressure, let us understand how the pressure is exerted on one piston and it is affected on another piston. So let us understand the first case. In first case, it is given that a force exerted on larger piston when a 10 Newton force is applied onto the smaller piston. So here the pressure is transmitted through the fluid that is undiminished, and that's why the equation we are having F2 equals to PA2, and P we are having pressure that is based on the applied force generated pressure on first piston, that would be F1 by A1, and the resultant equation we are having F2 equal to A2 by A1 into F1. We are having diameter of both the pistons. Based on that, we are able to calculate its area, that is pi r square. Diameter is given to measure to get the radius, divide by 2, so that would be pi r square. For A2, it means that is for the larger piston, and A1 that is for the smaller piston. So by substituting the value of diameter, we are able to get the area of both the piston, and the applied force is given, that is 10 Newton. By substituting all the values, we are having generated force F2 equal to 90 Newton. Now the second case is there, in which it's given that if a smaller piston is pushed in through a 6 cm, then how does the larger piston move? Here we need to calculate by which at which distance that larger piston will move. So here water is incompressible, so volume covered by that smaller piston, movement of that smaller piston inward equal to the volume moved outside due to the larger piston, that is L1A1, that is volume of first piston equal to volume of second larger piston, that is L1A1 equal to L2A2. Make the subjective formula L2, that would be A1 by A2 into L1. Areas we have already calculated. A1, that is the area of smaller piston, A2, that is the area of larger piston, and L1, that is the distance covered by the smaller piston. It is given 6 cm. Convert into the meter, it would be 6 into 10 raised to minus 2 meter. By substituting all the values, we are able to get L2 equal to 0.67 centimeter. So here atmospheric pressure is the same on both the piston, and very smaller variation available by the distance covered of the larger piston. So here these changes can be very much small. Next example, in a car lift, compressed air exert a force F1 on a small piston having a radius of 5 cm. This pressure is transmitted to a second piston of a radius 15 cm. If the mass of the car to be lifted is 1350 kg, then calculate F1. What is the pressure necessary to accomplish this task? Given G 9.8 meter per second square. So here pressure transmitted is undiminished throughout the fluid. The same equation we able to get it. F1, here earlier equation we have used F2 equal to A2 by A1 F1. Instead of that, make the subject of formula F1 that we need to calculate on a smaller piston. So F1 equal to A1 by A2 into F2. Now area A1, that is the area of smaller piston having a radius 5 centimeter. A2, that is the area of second piston that whose radius is given 15 centimeter. So here pi r square, which gives you the area of both the piston by having that equation. F force, that force by the car, it is available, that is 1350 Newton. So by substituting all the values over here, we are having F1 equal to A1 by A2 into F2. And F equals to mg. M is given 1350 kg. G is given 9.8 meter per second square. So by substituting the values of area and generated force by the car, we will get F1, that is 1.5 into 10 raised to 3 Newton. Here the air pressure will produce this force F equal to F1, P generated pressure P equal to F1 by A1. F1 we have calculated, A1 that is a pi r square, area of small piston, that would be equal to 1.9 into 10 raised to 5 Pascal. That is double than atmospheric pressure. Now let us understand what is streamline flow. While the fluid is in motion, we need to understand that fluid in a motion, that is the fluid dynamics. So here the motion of fluid, that is nothing but various fluid particles at a particular point in a space at a time. So the flow of fluid is said to be steady if velocity of each particle remain constant. But velocity of particle may change as it moves from one point to another point. So here the point of the particle may have a different velocity, but every other particle which may pass the second point, they behave as same as the previous particle. So each particle follows a smooth path, and the path of that particles do not cross each other. Here, which defines the streamline flow, the path taken by a fluid under a streamline flow, which is known as steady flow, that is known as a streamline. I repeat, the path taken by a fluid particle under a steady flow is known as a streamline. Here a curve is tangent at any point which gives the direction of the fluid and velocity at that point. Here in the diagram A, we can see the curve which defines the fluid particle moves with particular time. The curve PQ, this is like a fluid flow. It defines how the fluid streams available. No two streamlines can cross each other. If they do, then fluid particle can go either of the way in any of the direction, and flow cannot define steady. So for the steady flow, that is defined, that streamline, not going to cross each other in a particular time. Now you can see the diagram B, in which the planes perpendicular to the direction of flow of fluid, which is indicated as P, Q and R. This fluid particles crossing the surface, that is P, R and Q, is same. The same number of fluid particles entering from point P, and these particles will reach up to Q by passing the region R. But as we can see, cross-section areas AP, AR and AQ are not same. So based on that, their velocity or speed of the fluid particles that is available, VP, VR and VQ. So the mass of the fluid which cross the AP area in the smaller interval of time delta P, that is rho A V delta T. For the cross section area P, we can define as rho P AP VP delta P, as you can see over here, rho P into AP into VP into delta T. And this mass of fluid, that is delta MR, passing through the AR in the time interval delta T, that would be rho R AR VR into delta T. And the mass of fluid which pass through the mass of fluid, that is a delta MQ, which cross the AQ cross section area, that is rho Q AQ VQ into delta T. So here the mass of liquid, as we have defined, it would be same mass of liquid flowing out. So this all the values would be equated. So rho P AP VP delta T equal to rho R AR VR delta T equal to rho Q AQ VQ delta T. So based on that, we can say that for the incompressible fluid, that is a rho P equal to rho R equal to rho Q, the density of the fluid is same. Based on that, we can say that if density is same for the given time interval delta T, then APVP equal to ARVR equal to AQVQ. This equation is known as equation of continuity, and it defines the conservation of mass in flow of incompressible fluid. So here we can say that A into V, that is equal to constant. This AV gives the volume, flux or flow rate, which remains constant throughout the pipe. So at a narrower portion, the streamlines are closely spaced. At that point, the velocity of fluid particles is higher. And if AR, area is more, then velocity of fluid particle is less. So here, based on the area and velocity, the change in pressure generated, which gives the fluid flow in the horizontal pipe. Steady flow can be achieved at a low speed of flow. So beyond this limit, that is known as a critical speed, these steady lines cannot be defined and it becomes turbulent. Clear? Here we are going to end this session. Hope you understood. Thank you.